Let's talk about GPU instruction bandwidth. So remember the picture I showed you before. We've got all these processor pipelines here. We've got one instruction cache. And these GPU compute units here, they're going to fetch one instruction per cycle, but I've got all these different pipelines. So they take that one instruction they fetch per cycle and they share it with 8 processor cores. So you should be looking at this being a little worried. Well, okay, this will be fine as long as they're all doing the same instruction, but what if they don't? So if we don't all want the same instruction, this is known as divergent execution, and it can have really significant performance impacts on your GPU code. So let's take a look at this. Here I've got some instructions my threads are going to execute. They'll do number 1, number 2, then they'll do this if. If the if is true, they'll do 3, otherwise they'll go to the else and do 4, and then continue on 5 and 6. So here are my cycles, here's what I'm going to fetch from my instruction cache, and here are my threads that are running together on this processor. So I first start out fetching instruction 1, all the threads do instruction 1. Fetch instruction 2, all the threads do instruction 2. Fetch the if, all the threads do the if, that's fine. Now we're going to figure out which threads take that if statement, take that branch. Turns out only 7 of them do, so 0 through 6 take it, but 7 doesn't. So thread 7 here is going to stall. It can't fetch an instruction in this cycle because we only fetch one at a time. So thread 7 stalls, that's fine. Then on the next cycle we go fetch the else. This is where things get bad. All of these 7 threads now stall here because none of them want to do the else. In fact, I've only got one thread here that's going to do the else. Then we go on to do instruction 4, and the same thing happens here. I stall 7/8 of my threads. Well, this one thread that went a different way is processing. Now eventually we get through all the code here, and we continue. So all these threads wait to reconverge. Here's instruction 5. Now they can get back together. They all go back to do 5, and I get good throughput. And I go on to 6, and I get good throughput here. So what you see is there was a period here we had one thread that did something different, had a divergent execution, and it gave us enormously lower efficiency. Here we're getting 1/8 of our processor efficiency because only one of our 8 threads is able to execute. So divergent execution can really hurt your performance today. You really want to avoid it, and it depends on the GPU just how bad it is. So let's take a look at this for real. Here's a standard Mandelbrot calculation. You go around in this loop. For every pixel, you do this calculation. If the calculation works out a certain way, you get this value less than 4, then you return, and the color is the number of iterations you've been in. So if we take a look at what's going on here, color is determined by iteration count, and each color is a different number of iterations. So here's all the pixels I'm generating. I'm going to run all of these ones in parallel together, and what you get here is every different color here is a divergent execution. Every different color means a GPU thread went for a different number of iterations, so it did a different execution path. So something that is as wonderfully data parallel as Mandelbrot is actually not a great example for GPUs because it has this really divergent execution behavior. Now, instruction divergence. Some architectures are worse. So Intel Xeon Phi is 16-way SIMD. So that means if you don't have 16 SIMD instructions, 16 that are all doing the same thing at the same time, you lose a huge amount of your performance. They have a bunch of options in the compiler and a bunch of ways of masking out bits where they claim they can get a lot more efficiency out of this, but fundamentally if you're not doing 16 things same way at the same time, you're going to lose a lot of performance on Xeon Phi. Some architectures are getting better. So with Fermi, NVIDIA can fetch 2 instructions per cycle. So you might think, hey, this makes it half as bad. The problem is it has twice as many cores. So it's actually no worse, but it's also no better. The if-else case they can handle perfectly now because they can fetch 2 instructions, but if you actually have threads doing significant divergence, it's just as bad because they have twice as many cores. In general, purely data parallel code will always be fastest. That is, if all your threads are doing exactly the same calculations, just on different data, you'll get the best performance. And the penalty for having this divergent execution really varies. On NVIDIA's architecture, it can be pretty low if only a few threads diverge, whereas on AMD and Intel, it can be very significant even if just a few threads diverge.